Good morning. So just a few quick announcements before I get started with the course. The initial deadline for Lab 2 hasn't changed, so the actual deadline is today. We, however, have added 2 extra grace days without any strings attached. So that's that. Quiz 3's deadline is tonight, so pay attention to that as well. And then today in the afternoon, I'll do the demo for Lab 3. It's going to be really short, as I announced in the email I sent. So it's going to be short. It's going to be a build up on top of Lab 2. There'll be some extra interrupt handling that has been added to Lab 2. So and we'll have 2 terminals. So I'll talk about those. Now, with regard to grading, I was informed about some bad practices, if you wish. But anyways, we have revised the grading process for Lab 2, 3, 4, and 5. So I'll talk about that as well. It's good that everybody is on the same page, what you need to expect us and what we expect you to do for the demos. So there will be a discussion about that as well. Okay, so if there are, I see questions being posted already. What's going on with the grading for labs? Yeah, I'll talk about that during the manual, the tutorial. Okay. Now, okay, so we were discussing round robin. The last thing that we discussed was that if the time quantum, the length of time quantum goes to infinity, then round robin becomes first come, first serve. Now, let's answer a question. Let's see how context switching, how the time of the length of quantum can impact response time. So here is the question. So assume that the context switching overhead is 0. So let's put that aside. Now I'm going to play with the size of time quantum, the length of time quantum, and I want to see how that affects the response time of my system. So is the average response time always going to decrease if I decrease the time quantum? Or is it going to increase? Or would it depend? Sometimes it can increase and sometimes it can decrease. So which one is correct? Now, to answer that question, let's look at some examples. So let's say we have 2 tasks. So this is our workload, T1 and T2. And then let's say that time quantum is 10. What you can see is the schedule that would happen, and the average response time would be 10.5. Now, if I decrease the time quantum to 5, then this is going to be the schedule. So T1 is going to be divided into halves compared to the case where time quantum was 10. And average response time is going to decrease to 8.5. So it's going to be in favor of T2. Now, This is one case where we decrease time quantum, the length of time quantum, and the average response time actually went down. Now let's look at another case. This is another workload. If time quantum is 10, this is going to be the schedule. Both T1 and T2 are not going to use their entire time quantum. So this is going to happen. Average response time is going to be 1.5. If you decrease the time quantum to 1, again, you will get the same schedule. And average response time doesn't change at all. Now, let's look at the third example. I haven't changed the workload. It's still 1 and 1. This is what we saw with time quantum 1. Now, what happens if I have time quantum 0.5? In that case, as you can see, average response time actually goes up. So we're context switching between T1 and T2 every half a unit of time, and the average response time in this case becomes 1.75. So this is the third case where decreasing the time quantum has led to an increase in average response time. So if we go back to the question I raised at the beginning, the answer is it will depend. It will depend on your workload. What's going to happen if you decrease the average response time? If you decrease the length of the time quantum. Okay, now to finish our discussions, how do we actually use the time quantum? I alluded to this at the beginning. Usually what you do, you measure, so let's do it historically. It was actually around 1 second initially in Unix systems. But soon enough, they figured that that wouldn't lead to really responsive systems. If time quantum is 1 second, that's not responsive at all. So like if you were to press a key and there are some other tasks in front of you, then, and suppose that your key is going to be processed, or be shown on the screen after 3 seconds. That's not something that you would appreciate. Today, it has a range between 10 millisecond to 100 millisecond, somewhere in between there, and it would depend on the context switching overhead. So you would measure your context switching overhead and try to make that overhead to be about 1% of the time quantum. So if it is 1 millisecond, your overhead, then you want your time quantum to be 100. This is just rule of thumb. There is no math or there's no analytical, proof behind it. It's just common sense that you want to minimize the overhead, and like you want the overhead to be about 1%. So that's that. As we will see, the idea of round robin. So this is round robin vanilla version, where you just switch between tasks. You can add all sorts of extensions to this version, right? You could make some tasks have higher weight than others. So we'll see a version of that. So there are many extensions to this, but the idea of time quantum has been used in really many different scheduling algorithms, and we'll see some instances of that in the coming slides. Okay, now let's compare FCFS and round robin. So assuming that there is zero context switching overhead, is round robin always better than FCFS? So this is a loaded question. What do you actually mean by better? Now, there are different aspects that we can look at. If you remember, are you talking about performance? Are you talking about fairness? Now let's look at both of them. So here is an example to compare. At this point, let's compare performance, FCFS versus round robin. We'll later on talk about fairness as well. So with FCFS, let's say you have tasks 1 to 10, and each one of them takes 100 seconds. And let's assume that the time quantum with round robin is 1 second. Now, FCFS just does first come, first serve. Let's say T1 is first, T2 is second, all the way to T10. So this is going to be the schedule for FCFS. And if you do the math, I guess we're going to do the math later. Now, what happens with the round robin? With round robin, you're going to context switch every 1 second. Now, what becomes the completion time? So these are the completion times for FCFS. What about round robin? So with round robin, we're going to drag all our tasks all the way to here, because we're going to do a little bit of each one all the way throughout this 1,000 seconds. And task 1 will finish here, 991. And nothing happens with regard to task T10 in terms of its completion time, but other tasks are going to be dragged to this last 100 seconds. And as a result, the completion time of task 1 is going to be 991, 992, and so on and so forth. So just comparing these two numbers, FCFS looks a lot better in terms of response time, average response time, because all of these numbers sort of have now become more than 990. So there is not much change in terms of throughput. You still are completing 10 tasks per 1,000 seconds, so no change in throughput, but average response time is much worse under round robin. One other problem that you might face in real systems with round robin and really short time quanta is the issue of cache reuse. So what is cache reuse? So as we will discuss a lot more in the future lectures, the memory is hierarchical. We saw this at the beginning of the course, where I talked about how accessing memory, the time increases as you go from registers to first level cache, second level cache, to your memory, and then later on to your hard disk drives, your permanent storage. So the time goes up, access time, and the capacity also goes up. So you have like a handful of registers, but then your permanent storage is like terabytes, right? So cache is basically a memory that is close to the to the processor, and it can contain data that has been used by the running thread. We want to cache the data so that, because we see that data has locality, meaning that if a thread accesses a data now, it probably will access the same data a little bit later, or it could access data close to that piece. Maybe it's like a linked list, or maybe it's an array. So locality exists in memory accesses, so we're going to use that to cache data. Now, caching will help the performance of our applications because they can access memory instead of going all the way to the memory or to the hard disk. They could just access the cache. However, cache is small, so it cannot contain all the data. We have to evict data if new data wants to come in. Now, if you context switch between your tasks pretty frequently, you will end up not using your cache, because one of them will cache its data And before it gets a chance to reuse that data that is being cached, it will be evicted and the new one will come in. And then the new one will start populating the cache. And then once the time comes for this new one to use the data inside its cache, we're going to evict that as well. So if you have round robin with really short time quantum, with the length of time quantum being very short, this could actually mean that you're not using caches. So cache reuse goes to almost 0. And as we will see, actually, in some cases, introduces overhead just to populate the cache. Now, let's go back to the example that we started with round robin in the first slide that I had round robin. I got a question here. Just wondering for the last slide, why is round robin better? Don't they finish at the same time? Why is round robin better? Actually, round robin is not better when it comes to response time in that example. So throughput is the same because we finished 10 tasks in 1,000 seconds, but response time, as you saw, was much better with FCFS than round robin. Okay, so if you remember that example, we had 4 tasks and they each had different length. Now, this is the best case scenario with FCFS. If T2 comes first, T4 comes second, T1 comes third, and T3 comes last, basically, if the order in our queue for FCFS is according to the length of the tasks, then first come first serve gives you this. Again, this depends on the order that they come. This is the best case scenario that they could come. That T2 comes first, then T4, and so on and so forth. So in this case, the shortest task runs first, then T4, and then the longest task comes the last. And this gives you the best response time. So this gives you best FCFS. And the average response time is 31 and 1/4. Sorry, this is average wait time, and this is average response time. So you can do the math yourself. So this is best case. Now, what is worst case FCFS? So worst case FCFS is if the tasks come in the reverse order, in which case the waiting time for the worst case is 83.5, and the worst case response time is 121. So you can see the huge difference between best case and worst case FCFS. Now we're going to populate this this table with different time quanta for round robin. Now let's look at this case where the time quanta is the length of time quantum is 8. Basically, the shortest the shortest task was 8, right? This T2 guy was 8. So let's start with 8. And if you can see here, P2 only runs here and gets done, and then you're just context switching between different tasks. And if you do the math for time quantum size of 8, this is going to be your numbers. Now, we're not going to do the rest of them one by one. You can see how it works. You can do it at home for different time quanta and see what happens. Now, once we populate this list, it's actually interesting to look at some of these numbers. In particular, let's focus on T2. T2 was our shortest task, right? Now, if you look at T2, which is our shortest task, you can see that the wait time differs quite a lot for different time quanta, and so does the response time, because they're very much related, right? Now, what was our longest task? Our longest task was T3. Now let's look at T3 now. So if you look at T3, you can see that for different time quanta, the wait time is precisely the same, and so is the response time. Now, this actually means should mean something to you right now. So you can see that like this example shows you that if you're a long task, you're the least affected task when the response time, when the size of time, the length of time quantum changes. And if you're the shortest task, you're the most vulnerable or most affected task when it comes to the length of time quantum. Because it makes sense, right? If you're a short task, all you care about is the first time you get it, because you're going to be done, right? And the first time you're going to get it is going to depend on the length of the time quantum and how many tasks are in front of you. Whereas if you're a long task, it doesn't really matter. You're going to finish the last one, so it doesn't matter how many tasks are interleaved between you and then, as the length of the time quanta changes. The length of the time quantum changes. Okay, now let's move on to, so this should set the stage for the third algorithm, the third scheduling policy that we want to talk about. And the third one is shortest task first scheduling. As the name suggests, we're going to pick the shortest task in the queue, in the ready queue, and run that task. So this is actually provably the best algorithm when it comes to response time. I guess there's a slide for that. There is a variant to this. Sorry. So there is a variant to this called shortest remaining time first. So shortest task first is the version that is not preemptible. So you start running the shortest task, and once that's done, you go to the next shortest task in your queue. But if you have preemption, let's say you started the shortest task at the time, but another task comes that is shorter. But what does that mean, shorter? It means that the time that it takes to finish that newcomer is less than the time it takes to finish the current task. So that would be shortest remaining time first. In that case, you preempt your currently running task, and then you context switch to the shortest task. So that becomes the preemptive version of SGF. So these are the two. We usually are interested in the second one, where you preempt. Usually not usually, in this course at least, when we say SGF, we're considering the current CPU burst, right? We're not going to look into the future. So we look at the current CPU burst and we judge based on that. We're not going to look at what is going to come next. So the current CPU burst, what is the length of your current CPU burst, and that's what I care about. You might have shorter or longer CPU bursts in the future, but I'm not going to worry about them until you go out to I/O and then come back. When you come back, I'm going to look at your next CPU burst to judge which task to run. So very similar to what we have seen. If you are a short task, then this is gonna be in favor of you. And if you are a long task, this actually puts you in danger of a starvation. Okay, so as I mentioned, SGF and SRTF, both of them are optimal, meaning that they would minimize the average response time for any given workload. There is a proof for that. I'm not going to actually spend time on it, but you can actually prove that it's true. Now, let's do some discussions. Now, if we compare SRTF with FCFS, which one do you think is better in terms of performance? Now, is FCFS always, I mean, we saw that SRTF optimizes or minimizes the average response time. So we have a proof, mathematical proof for that. And FCFS doesn't. But does that mean that FCFS is always worse than SRTF for all workloads? And the answer is no. So if you have tasks with the same size, with the same CPU burst, then SRTF does the same thing that FCFS does. Does that make sense? So if your tasks are of the same length, then FCFS does one scheduling, and then SRTF also does that same scheduling. So FCFS is as good as SRTF. But if you have tasks with varying length, then, well, you have a proof that SRTF is better because it minimizes, and you don't have any proof for FCFS. It will really depend on the order of the tasks. Now let's run through an example comparing FCFS with round robin and SRTF. This is one of those examples that you have reoccurring behavior. So let's say that we have two tasks, A and B, and let's assume that A and B are long, really long, like it's just CPU burst forever, let's say, for a week or so. And then task C has a repeating behavior. So it does some CPU computation, and then it does some I/O. That sum is basically 1 millisecond. So C does 1 millisecond of CPU burst, and then followed by a 9 millisecond of I/O burst, and then repeats this behavior. Now let's check what happens under each one of these scheduling policies. So, actually, let's analyze this further. So if we just run A or B by themselves, the CPU utilization is going to be 100%. You're going to just always use CPU. But I/O utilization is going to be 0 because none of them is doing any I/O. So you're not going to be doing any I/O. If you run C by itself, then your CPU utilization is going to be 10%, as you can see here. So only 10% of the time you're using your CPU. What about your I/O utilization? Is going to be 90% of the time you're going to be using I/O. Now, we certainly want something in between, right? That we're both utilizing our CPU and utilizing our I/O. Let's see if any of these scheduling policies would achieve that. So what happens under FCFS? Well, the story is short and somewhat sad. The moment, I mean, it really doesn't depend where C is. C could be the first one or the third one, it doesn't really matter, or the second one. But the moment A and B get to run, they're going to just run forever, and C is going to be deprived of CPU until A and B are done. So it's terrible when it comes to average response time, specifically for C, because C will have to, the first one it runs, the moment it goes to I/O, A or B will get the CPU, and then when it comes back, it has to wait for A and B to finish. So very sad story for C. Now that's FCFS. What about round robin and SRTF? It's easier to see it with a timetable. Let's with round robin, we have to first talk about what is the length of time quantum. Let's start with 40 millisecond first. So with 40 millisecond, let's assume that C is first, then is A, and then is B. So let's say that's the initial order in our queue. So C is gonna run for 1 millisecond. It doesn't need its entire 40 milliseconds. It can, because its CPU burst is only 1. Then right after that, it goes for I/O for 9 milliseconds, and at this point it will be done. So it will come back. It goes to the end of the queue. So now you have A running, B waiting, and C at the end at this point. Now A runs for the entire 40 milliseconds because it can use it. It's not going to yield or give up the CPU time. Then we interrupt C. Let's say we set a timer goes off. We interrupt A. Next one in line is B. So B runs for 40 milliseconds, then A, and this repeats. So if you look at CPU utilization, it's 100%. All the time we're using CPU, but what about I/O? I/O is about 11%. Now let's reduce the time quantum, the length of time quantum, to 1 millisecond. Which is precisely the execution time, the CPU burst of C. Now C runs, goes for I/O. While it's going for I/O, A and B context switch. So A runs for 1 millisecond, B runs for 1 millisecond, A, B, and then eventually C is done. C comes, goes behind B or A. I don't exactly. It goes behind B. So B runs, and then this cycle continues. So now if you look at CPU and I/O utilization, I/O utilization has improved dramatically to all the way to 82%. And CPU utilization is still 100%. Now let's look at SRTF. With SRTF, if you are a long task, you're going to be screwed. You're going to be having the lowest priority. So every time C comes back to the system, it will get the highest priority. Why? Because its CPU burst is less than A and B. So C runs, then goes for I/O. While C is doing I/O, A runs. Then C comes back. C has priority. C runs, and then A runs. And then A runs, and then A runs, and then A runs. At this point, you should actually know that A will run, not B, because you started with A. A is just getting shorter and shorter and shorter. So A will always get priority over B. Until A is done, then B can run. So this gives you 90% CPU I/O utilization and 100% CPU utilization. What are the problems with SRTF? Starvation of large tasks, high overhead if you have context switching time, then because of every time you get a short task, you're going to context switch. So you will have a lot of context switches, and that means that you have high overhead. So if the context switching time is non-zero, which in reality is not, then you'll get really high overhead with SRTF. And it's also unfair because of the starvation problem. Now, these are some downsides with SRTF, but it's not the main downside. The main downside is it's impractical. It's not practical to use SRTF because we really in reality don't know how long each task takes. We don't have any idea about future. So it's in real systems, you really don't know how much more time you're going to spend on this task. There is a difference that usually people get confused about. So you probably know the number of instructions that your task has, right? But is that all you need to know about its execution time? Not really. I can have a task with 2 or 3 instructions that takes forever. If you think about it, if you have a while loop, an empty while loop, that's probably 2 assembly instructions. You just come and then go back. So 2 instructions, but then when you start executing it, it's going to take forever. So execution time of it is forever. The other example I can come up with is memory instructions, right? If you have a load or store instruction that is going to bring some data from memory, that's pretty much only 1 instruction, but it will take time, and that time is usually random. So if your data resides in cache, you're going to execute that instruction faster. If your data is in memory, it's going to take a little bit more time. If your data is actually in the hard disk, it's going to take even more time. So knowing the other important example is if and else and switches, right? You might actually know your code. It has a bunch of if then else's, switches and switch cases, and you wouldn't know which instructions will execute until you start executing it, because you might have an if with a long execution afterwards, but that if never gets satisfied. So in reality, when you start running your program, you never go to that if. So by just looking at my code and analyzing my code, I cannot come up with an execution time for my task. So in reality, it's kind of like impossible to know exactly how long your task is going to take. And that's basically enough to make SRTF just a theoretical scheduling policy. That actually doesn't mean that we shouldn't study SRTF. We actually did study SRTF for a reason, and that is the reason we study it is it's a good benchmark because it's optimal. So we want to compare different policies with SRTF, see how, because this SRTF gives us a bound, how good average response time could get for any workload. So it's a good benchmark, but it's just theoretical. You cannot really use it in your systems. Okay, so one of the ways that people have tried to predict execution time of tasks, and this actually comes up a lot in large systems in data centers, in production sites. You might have actually done this in the past yourself in any of your co-ops. If you go to a company and they ask you to do a performance test or something, right? One of the things that people do is to just gather some data from the past CPU bursts, if you wish, and then draw some conclusions about what you should expect in the future. So one of the things is basically a running average or a moving average, right? So you basically observe your CPU burst in previous times that your task was scheduled, and you try to fit a model to follow this. And then once you have this model fitted, you can actually use it to predict what's coming in the future. Usually this is one of the instances that people use, is kind of like an exponential averaging. So you have this alpha as your parameter that you're basically setting. It's a number between 0 and 1. So sorry, before we end getting there, so this is the whole idea behind the prediction. So basically I have some instances in the past, my past CPU burst times, and I want to find this function that takes as an input all those histories and then gives me as the output a prediction. Now, for this f, people have used all sorts of different functions. You can even use, I mean, it will depend on the context at which you're doing this, but maybe a very simple neural network. But again, it will depend on the context. So you cannot train a neural network if you're running an operating system. For instance, it takes a lot of time to be trained and to speed out a prediction, and you don't have that much time. But anyways, that's another topic to talk about. But one of the simple ones that people have used is this exponential averaging with this only parameter that is just alpha. And it pretty much what it does is it puts a lot of weight on, I mean, depending on this alpha. Let's say if alpha is 1, basically the prediction for the new CPU burst is what you saw last time. So if your CPU burst last time was 2 milliseconds, this prediction says your new one is going to be 2 milliseconds as well. Now, if you move alpha to come close to 0, that means that you're going to actually disregard the previous one. And if it is something in between, you're going to put some weight on the previous data point that you have and your average last time, your prediction last time. So you put some weight on your prediction of last time, and then you put some weight of what actually happened. So this is what you predicted last time, and this is what happened last time. You put some weight on each one of them to get your prediction. So there are many different cases that you can actually, many different functions that you can use in this context. Now let's talk about application types, because this is also important. This is a side, but we'll actually come back to this point later on when I discuss, I think it's when we talk about multiprocessors, where I will give you a history of Linux schedulers. We'll come back to this application types. Why is it important? People have tried, this is a side, so people have tried to use past burst times to somehow classify application times. You will see why this has been done later on, but now that we're talking about prediction and CPU burst time and such, it's a good time to think about this. So what people have thought about is, if your CPU burst time is really short, I should get some knowledge out of knowing that your CPU burst times are short. One of the things that that short CPU bursts could imply is that maybe you are an interactive application, like something like some application that interacts with users. So user gives you an input, you do some computation, you come back for the next one, right? So, or maybe it's a game, or maybe it's you know, some streaming. So it has really short bursts but long IOs. Now the question is, although this might be true for some applications, can you really generalize this? Can you really say if your CPU bursts are short and you have long I/O, that definitely means that you are an interactive application. And the answer usually is no. Again, later on, you will see why people wanted to do this. To just give you an overview, it's important to detect interactive applications because these interactive applications are the applications that we actually want to give priority to. Because when they're interactive, you want user to feel no lagging. So you want to give these tasks highest priority. So people are interested, system designers are interested in detecting interactive applications. Now, this particular way of detection, just looking at previous CPU bursts, turned to be a bad way of doing it. In particular, sometimes you might misclassify an application. So you might think because of its past behavior that it's interactive, and it's actually not interactive. And you give it some priority. That means that you're going to deprive others from priority, and those others might, one of them, be indeed an interactive application. And by just this misclassification and then changing your scheduling policy based on that, you might change the behavior of your applications. And that will become a sick and not useful cycle. So you misclassify, your misclassification leads to misscheduling, and then your misscheduling leads to behavior that is not normal, and then you use that not normal behavior to again classify, and this is just a bad cycle, right? Starting from misclassification to misbehavior, and then again misclassification comes afterwards naturally. And we will see that this actually happened in one of the previous versions of Linux scheduler. And this messed it up. They had to change the entire scheduler. Yeah, I actually have it here. O1 scheduler, which we'll see, was one of the ones that used something like this, and it led to many difficulties. So the idea was let's make O1 scheduler give more priority to interactive applications. In reality, what happened was people preserved O1 scheduler as unfriendly to interactive schedulers because of this misclassification. So the intention was to give interactive schedule applications some more priority, but because of the bad classification that was used or whatever, it ended up disfavoring. Is that a verb? Or not favoring interactive applications at all. Okay, so the bottom line with this SRTF is it's not really usable in reality, but it's a good benchmark. So it's optimal. It's hard to predict future. It could lead to too many context switches, and it could lead to a starvation and unfair allocations. And that's pretty much what we have to say about SRTF. Okay, now, what time is it? Okay. Next in line is a strict priority scheduling. This is the one that you're actually implementing for Lab 2. So you should be pretty much familiar with it. So this is just conceptual, talking about it conceptually. It's not about implementation of it, right? So what you're seeing doesn't imply any, it shouldn't imply any implementation. It's just conceptual. So conceptually, we have a bunch of priorities, priority 0 to whatever. And then you might have different tasks with the same priority, but then listed or sorted in each one of these priorities. It's called strict priority because you're going to actually every time look at the highest priority runnable task to execute. So you're not even going to look at low priorities. That's where the strict comes. So you're not going to even look at how many tasks there are in lower priorities. All you care about is your highest. If there is no task in your highest, then you go to the next level, the next level, and the next level. So as long as you have tasks in high priority, even one task, that task is going to be favored over, you might have 1 million tasks here, and you wouldn't care. Now, how do you schedule within each queue? So with lab 2, what we asked you for each queue, we asked you to do first come, first serve, but that's not necessary. You could do round robin. You could do any other scheduling policy you want per queue. So conceptually, strict priority tells you to focus on the highest priority with runnable tasks. But then how do you do within those tasks? There are variants to that. You can do first come, first serve. You can do round robin or whatever you want. What are the problems with this? Starvation is the big one, right? If you probably have seen it in even the starter code we gave you, it creates a user task which never runs because it has low priority. So you could starve low priority tasks. Priority inversion could also happen. We'll talk about it later on. So I'm just leaving it here so that later on, if you come back to these slides, you know what's wrong with it. We'll definitely talk about this in the context of real-time systems, and you will see what it exactly is and how we can actually deal with it. Now, okay, so that's pretty much it in terms of basics. Now, let's up our game a little bit, talk about different criteria and different ways to address them, coming up with some, some more fancy scheduling algorithms. So let's focus on fairness and see what we can do with fairness. So the strict fixed priority is really unfair. What else did we see that was really unfair? The shortest task first also was really unfair to long tasks. And then comparing round robin and FCFS, it felt that round robin was more fair by just context switching between the tasks. And then first come, first serve was, okay, whoever is first, they're going to get. So far, we haven't seen really any scheduling policy that precisely addresses the fairness problem. So that's what we want to focus on. This is actually a nice anecdote. This strict fixed policy, strict fixed priority scheduling was implemented in one of the early Multics systems. If I'm not mistaken, from MIT. If I'm not mistaken, I think. I might be wrong, but pretty sure it was MIT. When they shut down their system, they found a 10-year-old task there sitting because of its low priority never ran. So that's a cute little fact or history. Now, how can we make a fair scheduler? We can take one of these and try to make it fair. Let's start with this strict policy. How do you think we can make it fair? Well, one way to make it fair is instead of doing strict priority, meaning that we only look at the first queue, and if it has tasks, we're not going to go down. you could do round robin between the queues, for example, or you could dedicate some portion of time. Let's say in every minute, you spend 45 seconds on serving tasks from priority 1, and then for the remaining, you divide that to priority 2, 3, and 4, for example. So that way, you're sure that in every minute, your high priority tasks got collectively 45 seconds, let's say, and low priority tasks, they all shared the 15 seconds, the remaining 15 seconds, or something along those lines. So somehow, don't get stuck with the high priority. Sometimes move on to the other ones and serve them as well. So that's one idea you could do. And indeed, it actually was implemented, something like that, in a variant of this was implemented in some early Unix systems. So I guess I have it. Yeah. This variant is called multi-level feedback queue. And the idea is have this high priority task, high priority queue at the top. And then some other queues. You could have, in this example, I have 3 queues in total, but you can have as many queues as you want. What you do is, what I'm actually now describing is the vanilla version that was initially implemented. You can change that. It's very flexible. But let's just talk about the vanilla version. The vanilla version had round robin in all the in these 2 queues and FCFS in the last queue. The way it worked was the highest queue had really low, really short time quanta. And then the second one had longer time quanta, like 16. And the last one had the time quanta was infinite, basically, because infinite, if you remember, infinite time quanta means FCFS. So basically, as we come down the list, the time quanta, the length of time quantum increases. Now, how do tasks do? So every time a new task comes, they go to this first queue. And when I say every time they come, it means every time they come from I/O. If it is a new task, it doesn't really matter, right? Every time they come, they go, like they might do some computation and then go for I/O. Whenever they come back, we put them back in the top. Now, they get a short time quanta, the short time quantum here. Now, if they are interactive tasks with short CPU bursts, that should be enough to get them going. So they would be done. They would go and do some I/O and then probably will later on come back. If they're not actually interactive and if they have like longer CPU burst, once they're done with this time quantum, we'll put them back to the second queue. And when they're done with this one, they come to the third queue and then wait here until it's done. So as you can see, the idea here is to get something between shortest task first and FCFS. So we want to create this spectrum of tasks, and we want to somehow get the benefit of both worlds. We don't want to predict about the CPU burst, so we're not doing any prediction, but we still want to have interactive tasks scheduled first and fast, which this does for us. So when do we start doing things here in the getting tasks out of here? We're still doing it when there are no tasks here. So if there are no tasks here, we come to the second task and serve tasks here. And when there are no tasks here, we come here. So it still has some starvation on unfair. So if you could imagine, if you keep getting new tasks, so if you keep getting new tasks, these two queues are going to be starved. Okay, there are variants to this. You can add more than 1 or 2 queues. You can do different sorts of, like, how do you increase the time quanta, the size of time quantum from one queue to another? You can come up with all sorts of stuff that you might want. But what I just described was kind of like the vanilla version. Now, the vanilla version actually had some flaws. Yep, I actually described those. Okay. So yeah, so we talked about all of this, right? It kind of like it approximates SRTF, because if you're short, you're going to get higher priorities and get done. Now, the way you can actually do between them, as I mentioned, you can do fixed priority scheduling between the queues, right? Which is what I just described. If you don't have any tasks here, come to this or come to this, or you can do time slicing between them. The second one that I mentioned, like 45 seconds spent on this one, 5 seconds on this, 10 seconds on this one, and then 5 seconds on this one in every minute, something like that. So it's very, very, very flexible. You can come up with different versions. Now, the part that I wanted to talk about, which is kind of interesting, is, and related to my research when I was a PhD student, is mechanism design, really. When it comes to scheduling, you have to consider the incentives that your scheduler gives the tasks in the system. For instance, let's start with an example with Lab 2. So if you are a task in Lab 2 and you're a user of the operating system that you guys are writing, you always have the incentive to give yourself, you can set your own priority to the highest. So the moment you get the CPU, let's say other tasks are gone, you can increase your own priority to the highest and like just always run, right, without yielding the processor. So this is something that we always have to consider, that programmers, those who are going to use our system, are going to see and observe how the system works and then take advantage of it in their own benefit. Now, this benign scheduling policy that was indeed implemented in early Unix systems was abused by the programmers in a funny way. So this is actually an anecdote from MIT. So they had this Othello contest at MIT, where different groups were writing programs to play Othello. And if you have done anything with AI, you know that the more computation time you get, the more states you can visit, and the more informed decision you can make. So if you have more time to explore the state of the game, you can make better decisions and make better scores in the game. So one of the groups, or some of the groups, knew that the system is using this multi-level feedback queue. And the vanilla version that I just described puts you in this first queue every time you come back from I/O, right? So what they did was, quite frequently, they just called printf in their code. And what that printf was doing was basically doing a short I/O and then coming back to the high priority task. So they would prevent their task from going from this high priority to lower priority queues. So their task always remained on this high priority queue. So it got all the time. So it was making more informed decisions, and it was winning the games, basically. So that's kind of cute. But then in real system, real world, there are consequences of making wrong decisions as a system designer. So I just felt like this was one of the good examples. I actually have real examples from Yahoo, Google, that these things happened, right? Their own employees were just trying to, it's well documented by the two companies, that their own employees were trying to game the data center manager in the that was in place to get more resources for their tasks. So this is something to pay attention to, actually. I got a question here. For multi-level feedback queue, how does a task level leave a queue? For example, how would a task leave the first queue and go to the second queue? Well, when you get scheduled here, let's say it's your turn, you get to run for 8 time units, whatever that is, and then timer expires. If you're not done and you still have CPU burst, then you are moved to the second queue, and then you will wait for your turn to come here. Now the question is, how do you go from this queue to this queue? Well, you can do all sorts of stuff. So you can do strict priority, you could do time slicing, you could do round robin, and so on and so forth. So now that we're talking about fairness, let's talk about other scheduling policies. I'm going to be a little bit faster. So one of the most famous fairness policies is lottery scheduling. The idea is to give tasks a number of lottery tickets, and then at each time slice, that like you still have this time quanta. At the beginning of each one of them, you run a lottery. So you pick a ticket, and then you see who has that ticket, and then you schedule that task. So it's random, but on average, you will see that the number of times that a task is going to be picked will be proportional to the number of tickets that it has compared to others. So if everybody has that same number of tickets, then on average, you could get 1/n of the CPU time. If one task has twice as many lottery tickets as everybody else does, then on average, in long time, that particular task will get twice as much CPU time as others. Does that make sense? I have to correct myself. This depends on, this has an assumption that all the tasks have the same CPU bursts, right? Because you could have twice as many tickets as others, but if your CPU burst is short, then you will be scheduled probably twice as many times as others every time you're ready. So if you have a lot of tickets, but then you're always in the IO, and you're not in the ready queue, so your ticket won't win, right? But as long as you're ready in the ready queue, so meaning that you have a CPU burst to complete like others. So if I set the CPU burst to the same thing, let's say everybody has infinite CPU burst, and then someone has more tickets than others, then they would get more CPU time than others. Again, if I have a lot of tickets, but I'm short, the length of my task is short, it's going to get some CPU time and it's done, then I can't say much about how much CPU time I'm getting. So it all depends on the length of your tasks as well. But if you make it equal for everyone, then what I said holds. Now, how do we assign tickets? Well, as you might have noticed, the more you have tickets, the higher your priority is. Now it will then depend on what do you want to set as a metric for priority. Do you care about the length of the queue of the tasks? Do you care about some exogenous and external weighting system? Let's say this user of the system has paid me more than this one. I want to run the user who have who has paid Amazon, for instance, twice as much as the other one. I want that user to get twice as much resources. So I'll give that user twice as many tickets. So it could be exogenous. It could be, you tell me how you want to do this. It's good because of its randomness. To give at least everybody one ticket to avoid the starvation. Because if you have one ticket, on average, you're going to get 1 divided by the number of available tickets in the system. So you're going to be scheduled. So everybody will actually make progress. OK, now here's an example. I'm going to actually sort of move on. So it just shows you how this, like how tickets have effect on the percentage of CPU time you get. Again, it's just assuming that everybody has CPU burst all the time. So let's say we're going to give short tasks 10 tickets and long tasks 1 ticket. If we have 1 short task, 1 long task, then as long as the short task is in the system, because if the short task runs and finishes, then all the time goes to the long task. But as long as you have the short task in the system, the short task is going to get 91% of the CPU, and the long task is going to get 9%. And this is on average, right? On average, in a long period of time, if I look, then this is going to be the case. Now, if I only have 2 long tasks, then each one of them is going to get 50%, right? Each one of them has 1 token, so they're going to just divide. And if I have 2 short tasks, each one of them is going to get 50%. If I have 1 short task, if I have 10 short tasks and 1 big task, then all the short tasks are going to divide this with each other. This 91% is going to be divided between those 10. Sort of. No, actually, that's not precisely true, but similarly, right? So now you have each one of the short tasks is going to get 10 divided by 101, which is very close to 10% of CPU time. And that 1 long task is going to get 1 divided by 101, which is very close to 1%. So on and so forth. Now, the downside, so if you have too many short tasks, running lottery scheduling is not a good idea. The reason is it's random, right? So on average, you get what you're supposed to get. But if I look at every short window of time, you might not get what you're supposed to get because it's random, right? It's still possible that somebody with less tokens than less lottery tickets than you will get to be chosen in a long window of time. If I increase the window of time that I'm looking at my system, everybody gets on average proportional to how many tickets they have. But in short window of time, if I look, then that's not the case. So this is one example that shows that precisely. So let's say, let's define unfairness for 2 tasks with the same burst time. Let's assume that we have 2 tasks. They have the same burst time. And we want to measure the finish time of the first one divided by the finish time of the second one. So if they both finish at the same time, then this becomes like 1. And unfairness is 1. So the higher this so the finish time of the last one is always bigger than the finish time of the first one. So the closest this number is to 1, the more fair the system is. And the closer this number is to 0, the more unfair this system is. It means that although the two tasks have the same execution time, we favored one to another. Now, this figure is showing you this unfairness metric on the y-axis, and on the x-axis, it changes this. We said that these two have the same CPU burst time, so it changes the length of this burst. So starting from here, both of them have length 1, right? Let's say the time quantum is also 1. First one finishes at time 1. Second one finishes at time 2, right? So this unfairness becomes 1 divided by 2. It's half. Now let's start increasing this time, the CPU burst time. Get it to 1000. Now every 1 second we're gonna do the lottery. And if both of them are really long enough, then they probably will finish together, right? So this unfairness metric gets closer to 1. So as you can see, it's a number between half to 1. So it actually depends on the length of the CPU burst of these two tasks. If they're really short, this means that the window that we can focus on is short. So in short window, we don't get really actual averages. If they're long, then we can actually look at a longer window and we get on average fair system. So the title of x-axis is confusing. If the ratio is closer to 1, it should be more fair, correct? Yeah, it's not from, it's from a paper that did this. I agree with you. I would actually call it fair, not unfair. So if it is 1, then it's fair. If it is not 1, less than 1, it's unfair. But it's okay. Like I just was, I got this figure from a paper. So anyways, you got the idea, hopefully. Another question came up. In lottery scheduling, do we assume all tasks would have the same burst time for ideal performance? Let's not make any assumptions. So you know how lottery scheduling works. Now, I think in the quizzes, we will have to be really careful in laying out what the situation is, like how big the burst times are. But usually, because it's a random process, in order for you to get accurate results, you need long CPU burst times. Not necessarily the same, but you need to look at your system in the long term. Okay, I guess I only have 1 minute left. Oh no, I don't have any time left. So I'm gonna stop here. Thank you for those of you who have attended the lecture and those of you who have watched it. We'll talk to you next Tuesday. I mean, come to the lab tutorial today, but next lecture next Tuesday. Oh no, next. I think reading week is coming. So after the reading week. Yes, I think reading week is coming. So we'll talk to you after the reading week. Bye-bye. Take care. Be safe. Bye-bye.